Today we'll start our discussion on the next topic in the scope of the present course, that is industrial chimneys, as part of the second component of the course, that is based on industrial structures. Well, in structural terms, an industrial chimney is essentially a cylindrical shell. However, it would be useful to discuss the functional and historical aspects of the industrial chimneys so as to gain a perspective on the overall role and importance of industrial chimneys in the industry. The definition or function of a chimney is to discharge waste gases at a sufficient height with a suitable velocity so that the concentration of the gases and the entrained solid particulates, that is the pollutants, is reduced by atmospheric turbulence to environmentally acceptable limits before reaching the ground. A brief historical review of the development of industrial chimneys may be pertinent from the point of view of understanding the evolution of the structural design of industrial chimneys for purposes of construction in the industry. Well, the earliest form of chimney systems that were developed by humans to dispose gaseous waste products of combustion were brick vents. With increase in volume of gases that were to be handled, that is the discharge of the chimney, that is the volume of gases to be exhausted per unit time defined as discharged, increasing in magnitude. The brick vents were replaced by larger brick and steel chimneys. As the chimney size increased, the design process of the chimneys evolved to account for factors such as gas pressures, velocity effects, discharge or exhaust requirements, and corrosion of the chimney shell due to abrasive effect of the waste gases. It may be noted here that chimneys larger than 500 mm in diameter are termed as industrial chimneys. Continuing our discussion on the historical review of the evolution of industrial chimneys, the most popular shape or geometry of industrial chimneys that have been constructed in practice in the industry is the circular cylindrical shape or the circular cylindrical geometry, which is the most popular geometry and is therefore the only type or geometry or the shape of the industrial chimneys that is included in the scope of the present course. As the chimney heights increased and the draft requirements of the chimneys increased, the construction materials that were popularly adopted or favored as the materials for building the industrial chimneys also evolved. And with increase in the chimney heights, steel became the traditionally preferred construction material since the 1600s due to the superior mechanical properties of steel, including tensile strength, superior ductility, hardness, toughness, and the yield strength. Reinforced concrete was adopted as the construction material for industrial chimneys for the first time in USA, UK, and Europe in the 1900s. The first reinforced concrete chimney was constructed in 1896 in Germany. Concrete or reinforced concrete, however, was not popularly accepted as the construction material for construction of industrial chimneys because of the issue of cracking of concrete due to the thermal gradient, and it was only in 1950s when concrete or reinforced concrete became widely accepted as the construction material after the issue of the cracking of concrete due to thermal gradient was resolved in 1950s. In order to resist the thermal gradient in large brick chimneys, earlier, that is before the development of reinforced concrete chimneys in the 1900s, the masonry or brick chimneys that were prevalent earlier before 1900s were provided with a steel lining. Although the early brick chimneys were unlined, that is, the earliest brick chimneys that evolved from the small vents for exhaust of waste gases were unlined. The development of boiler and fuel technology in the 1700s forced the introduction of a liner, that is a protective lining, in the interior of the brick or concrete chimneys, which was originally composed of insulating bricks, as in case of steel chimneys, and later replaced by a steel liner, as in case of the concrete or reinforced concrete chimneys that evolved with the acceptance of reinforced concrete as one of the favored or preferred materials for construction of industrial chimneys. The figure here depicts the provision of a liner that may be visualized as a brick liner in case of the early steel chimneys in 1700s, as represented by the dashed green line, or the steel liner as in case of the reinforced concrete chimneys that were introduced in the 19th century or early 1900s, after reinforced concrete became popularly accepted construction material, after the design or practical issue, that is the practical problem of concrete cracking due to the thermal gradient, was resolved in the 1950s. The design process for industrial chimneys also evolved over the centuries, starting from the 19th century up to the present, and the currently prevalent design process for industrial chimneys consists of two fundamentally distinct stages or parts. That is, one, the functional design, in which stage the objective of the design process is to ensure that the chimney serves the intended function, that is, to discharge or exhaust the desired or design volume of waste gases with the required exit velocity and the desired thermal performance. And two, that is the second stage of the design process for industrial chimneys, is the structural design stage, in which the objective is to ensure that the chimney remains structurally safe and stable while performing the intended function mentioned earlier. The structural design of circular cylindrical concrete chimneys in India is performed in accordance with the design specifications and criteria specified by IS 4998, that is the Indian Standard Code of Practice for Structural Design of Circular Cylindrical Industrial Chimneys. It is worthwhile to note here that the functional design, that is the first stage of the design process for industrial chimneys, is in the scope of thermal engineers or mechanical engineers in general. However, the design process in entirety is interactive and iterative, as some of the parameters that govern the functional design also influence the structural design, and therefore in practice a trial and error design procedure is employed or required to finalize the functional design by the thermal engineers in interaction with the structural engineers who complete the structural design of the industrial chimneys. Further, the structural design stage, that is the second stage of the design process for industrial chimneys, is the stage or the part of the design process for industrial chimneys in which the base dimension, the thickness of the chimney shell, T, are decided with respect to the given height of the industrial chimney, that is dictated by the functional design requirements, to ensure that the stresses in the chimney shell at the base of the chimney under various design load combinations are within the permissible limits. Continuing our discussion on the design process for industrial chimneys, in the functional design stage, that is the first stage of the design process for industrial chimneys, qualitatively, the chimney is sized, proportioned, and dimensioned to ensure that the given quantity of flue gases are exhausted or discharged, that is, the volume of gases that are required to be exhausted or discharged per unit time with a suitable velocity termed as the exit velocity at a sufficient elevation, that is governed by the height of the chimney, such that the ground level concentration, abbreviated as GLC, of the pollutants, that is the waste gases and the entrained solid particulates, is diluted to the environmentally regulated limits by atmospheric dispersion at the selected height and the selected exit velocity. It is pertinent to note here that the discharge, that is the volume of the gases that are to be exhausted per unit time from the industrial chimney, may be related to the exit velocity of the flue gases or the exhausted or discharged gases as the product of the exit size of the chimney, that is the exit dimension of the chimney, times the exit velocity of the flue gases. Mathematically, therefore, the discharge or the volume of gases that are exhausted per unit time from the industrial chimney equals the exit area AE times the exit velocity of the flue gases VE, where the exit area denoted as A subscript E of the chimney is simply equal to pi times E square divided by 4, where E is the exact dimension or exact size of the industrial chimney in case of circular cylindrical chimneys. Hence, to summarize, the functional design parameters, that is, the parameters of the design process that are to be dictated or finalized in the functional design stage of the industrial chimney based on the above mentioned or above stated function of the industrial chimney are as follows. 1. The exit velocity of the flue gases, that is the velocity with which the waste gases are discharged or exhausted from the chimney, denoted as V, capital V, subscript E. 2. The draft requirements, that is the volume of the flue gases that are required to be exhausted or discharged from the chimney per unit time, which governs the thermal performance of the chimney or dictates the thermal performance of the chimney. Parameter that is in the scope of thermal engineers or mechanical engineers. 3. The exit size of the industrial chimney, denoted as small e. And 4. The physical height of the chimney, denoted as h subscript p, which dictates the height of the discharge of the exhausted gases or the elevation of the discharge of the exhausted gases to ensure that the ground level concentration, abbreviated as GLC, of the waste gases and the entrained solid particulates that constitute the pollutants is diluted to the environmentally regulated limits by atmospheric turbulence at the selected physical height HP of the industrial chimney. And finally, last but not the least, an additional and equally important functional design parameter are the environmental regulations or the environmentally regulated limits, that is the limiting ground level concentration or the maximum ground level concentration that is stipulated by the environmental regulations termed as the permissible GLC, or the permissible ground level concentration of the pollutants, that determines the functional design of the industrial chimney to ensure that the industrial chimney serves or fulfills the intended function stated earlier. On the other hand, the structural design parameters, that is, the parameters that are considered in the structural design stage, that is the second stage of the design process for industrial chimneys, are primarily the base dimension of the chimney, denoted as small b, the area of the shell of the chimney, that is the cross-sectional area of the chimney shell at the base of the industrial chimney, or the shell thickness, that is the thickness of the chimney shell at the base of the chimney, as well as the shape of the chimney in elevation, considering the taper that is typically provided in the elevation of the chimney, which is generally in the range of 50 to 100, that is the taper being generally in the range of 1:50 or 1:, up to 1:100. It may be noted here, as mentioned earlier, that the functional design and the structural design of the chimney, which are the two stages of the design process for industrial chimneys, are interactive in nature. In other words, the design process of the chimney is an interactive and iterative process, since given the discharge requirements in terms of Q, that is small q, denoting the volume of gases to be discharged per unit time, defined as the draft or discharge requirement for the industrial chimney under consideration, and the ground level concentration that is permitted, or the permissible ground level concentration, abbreviated as GLC, to which the discharge gases are to be diluted in order to conform to the environmentally regulated limits of the maximum or permissible ground level concentration before reaching the ground. The determination of the physical height denoted as HP, small h subscript p of the industrial chimney, and the exit velocity of the flue gases or the exit size denoted as small e of the industrial chimney at the top of the chimney is an interactive process, since the physical height HP of the chimney and the exit size of the top of the chimney will influence or determine the structural design parameters, which are the base dimension B and the shell thickness T of the cylindrical shell in the industrial chimney. While on the other hand, conversely, the structural design parameters, that is the physical height of the chimney denoted as H subscript P, and the exit size of the chimney at the top, will influence or affect the functional design parameters. And hence, the design process for an industrial chimney is an interactive and iterative process wherein for the given discharge requirement or the draft requirement, that is the volume of the exhaust gases to be discharged per unit time denoted as small q, and the permissible ground level concentrations, that is abbreviated as GLC max, that is to be achieved by the industrial chimney after exhausting or discharging the given volume of the flue gases at the given height, that is the physical height of the chimney, determines the physical height of the chimney and the exit velocity of the flue gases, which in turn governs the structural design parameters, that are the base dimension B of the industrial chimney and the thickness of the chimney shell, while the physical height of the chimney denoted as H subscript P and the exit dimension of the chimney that is part of the structural design process, or rather the functional design process, will in turn determine the functional design parameters. Continuing our discussion on the design process for industrial chimneys, even though functional design of industrial chimneys is in the scope or purview of thermal engineers or mechanical engineers who ensure that the industrial chimney under consideration serves the intended function of disposing or discharging the required volume or draft of waste gases at a sufficient elevation with a suitable exit velocity, so that the ground level concentration of the pollutants, that is the waste gaseous products and the entrained solid particulates in the discharged gases, conform to the environmentally regulated limits before reaching the ground after dilution or dispersion due to atmospheric turbulence. However, since the design process and the two stages of the design of industrial chimneys, that is the functional design stage and the structural design stage, are interactive and iterative in nature, some of the functional design parameters, such as the required physical height of the chimney and the exit size of the chimney, are common and overlapping with the structural design parameters, which are the physical height of the chimney, the base width of the chimney, that is the diameter of the chimney shell at the base of the industrial chimney, as well as the exit size of the chimney at the top, being common and overlapping factors between the functional design and the structural design. It is useful and informative for the structural engineers to have a intuitive understanding or insight into the physical relevance or the physical significance of the functional design parameters also, in order to interact effectively with the thermal engineers to ensure that the industrial chimney, thus designed after going through the functional design and the structural design stages, is able to achieve or serve the intended function stated earlier, while the chimney structure remains structurally safe and stable in order to serve the intended function. Hence, we will present or discuss a brief overview of the salient functional design parameters that are considered in the functional design stage of industrial chimneys, the most important of which is the exit velocity. That is the velocity at which the gaseous waste products or the exhaust gases are discharged from the top of the chimney as depicted in this figure on the present slide. In order to understand the physical significance of the exit velocity, denoted as capital V subscript E, of the discharged gases, or the velocity at which the waste gases are discharged from the top of the chimney, consider a chimney such as the one shown in the figure on the present slide, with the emanating gases exposed to a field of increasing wind speed, denoted as capital V subscript W, for example, wherein the notation V in general represents velocity or the speed, while the subscript W denotes the wind speed. And for a given exit velocity, denoted as VE, wherein the notation V or capital V represents velocity, while the subscript E signifies that the notation or the symbol V subscript E is the exit velocity of the gas plume or the emerging gases discharged from the top of the chimney. A critical wind speed will be reached at which the wind will shear off the emerging gas plume from the top of the chimney. That is, when the emerging gas plume is exposed to a field of increasing wind speed in theory. And when the critical wind speed at which the wind shears off the emerging gas plume, or due to the emanating gases exposed to the field of wind or airflow, is reached, then the emerging gas plume will result in the excessive deposition of pollutants in the airstream, which is undesirable. In other words, for a given exit velocity, VE of the emanating gases discharged from the top of the chimney, as the wind speed at the site of the construction of the industrial chimney increases, a critical wind speed will be reached in theory or in principle, at which the wind, due to the critical wind speed or the threshold wind speed, will shear off the emerging gas plume from the top of the chimney, thus resulting in excessive deposition of pollutants in the airstream, which is undesirable, which is therefore one of the functional design considerations or one of the physical phenomena that need to be considered in the selection of the functional design parameter, that is the exit velocity of the emanating gases, denoted as VE. Hence, intuitively, the exit velocity VE should be greater than the minimum threshold value, denoted as VE superscript minimum, for which the critical wind speed, denoted as VW superscript CR, at which the wind shears off the gas plume, thus resulting in excessive deposition of pollutants in the airstream, should be greater than the design wind speed at the site, in order to ensure that the wind does not shear off the emerging gas plume and result in the deposition of excessive pollutants in the airstream, which is undesirable. Additionally, if the exit velocity is too large, or too small, that is, if the exit velocity is too high or too low, then there are some additional implications on the performance of the chimney. In other words, for too high exit velocities or too low exit velocities, there are other additional design issues from the point of view of functional design of the industrial chimney. However, the most important or fundamental design consideration for selecting the exit velocity, denoted as VE, for the specific industrial chimney that is to be designed and constructed, is that the exit velocity should have a minimum value such that the exit velocity is greater than the minimum threshold value at which the critical wind speed, that is corresponding to the minimum threshold value or the minimum value of the functional design parameter, that is of the exit velocity, at which the wind shears off the gas flow, thus resulting in excessive deposition of pollutants in the airstream. Hence, one may interpret based on the physical reasoning or the physical phenomena underlying the shearing off of the emerging gas plume from the top of the chimney by the wind, that the exit velocity that is selected for the particular industrial chimney should be greater than the minimum threshold value for which the corresponding critical wind speed, that is the wind speed at which the wind shears off the gas plume, resulting in excessive deposition of pollutants in the airstream, is greater than the design wind speed, in order to ensure that the wind does not shear off the emerging gas plume from the top of the chimney. Since the design wind speed at the site, that is the actual wind speed at the site Vz at the relevant height Z at the top of the chimney is less than the critical wind speed that is required to shear off the emerging gas plume, which is an undesirable condition. Further, as mentioned earlier, there are additional functional design considerations for selecting the exit velocity as exit velocity that are too high or too low present other design implications from the point of view of functional design of the industrial chimney, due to the adverse effects of excessively high or excessively low exit velocity on the functional design of the functional performance of the industrial chimney. For example, if the exit velocity is too low when the chimney is operating at part load or zero load, as a relevant and practical situation, that is when the plant is inoperational, then in such a situation, when the chimney is operating at zero load, when the plant is inoperational, or even at part load, cold air may blow down part of the vent of the chimney, thus resulting in condensation of acidic content of the gases or the waste exhaust gases, leading to abrasive damage of the chimney lining due to the condensation of the acidic content of the waste gases in the chimney vent, which obviously is an adverse effect and is therefore an undesirable condition. Hence, one may interpret based on the physical phenomenon just stated, that is the physical condition or situation wherein cold air may blow down a part of the vent of the industrial chimney due to excessively low exit velocities, resulting in condensation of the acidic content of the gases and leading to abrasive damage of the chimney lining, that a minimum value of the exit velocity should be maintained even when the plant is inoperational or working at zero load. Summarizing our discussion on the most important functional design parameter in the functional design stage for an industrial chimney, that is the exit velocity, denoted as V subscript E. The various design considerations that govern the selection of the exit velocity V subscript E may be summarized as follows. The minimum exit velocity, even when the chimney is operating at part load or zero load, for example, when the plant is inoperational, should be such that the critical wind speed, denoted as V subscript W superscript CR, at which the wind is able to shear off the emerging gas plume from the top of the chimney, thus resulting in undesirable excessive deposition of pollutants in the airstream, is greater than the design wind speed, denoted as V subscript Z, at the height or elevation Z corresponding to the top of the chimney at the construction site of the chimney, so as to ensure that the wind speed does not exceed the critical or threshold wind speed that is required to shear off the emerging gas plume of the emanating gases from the top of the chimney. Hence, leading to the conclusion that the exit velocity denoted as V subscript E for the industrial chimney that is selected in the functional design stage of the industrial chimney should be greater than a minimum threshold value. Design charts are conveniently available to indicate the minimum exit velocities for different design wind speeds that may be pertinent for the particular construction site of the industrial chimney, for which the critical wind speed is greater than the design wind speed at the construction site of the industrial chimney as provided by IS 875 Part 3, that is the Indian Standard Code of Design Practice for calculation of design wind speeds and design wind loads, thus ensuring that the gases leave the chimney in a clean manner, and the design charts that provide the minimum exit velocities for different design wind speeds that may be relevant for the construction site at which the industrial chimney is to be constructed are presented in the annexure at the end of the lecture notes, or the annexure that is presented at the end of the present lecture series. In addition, there are other functional design considerations for selecting the appropriate exit velocity for the given industrial chimney, which are also mentioned in the annexure presented at the end of the current lecture series. For example, the functional design considerations that govern or dictate the maximum and minimum limiting values of the exit velocity of the emanating gases discharged from the top of the industrial chimney as presented in the annexure at the end of the current lecture series may be stated as follows: too large an exit velocity will damage the chimney lining due to the erosion of the chimney lining by the gases flowing with an excessively large velocity. As a result, based on the functional design consideration just stated, the maximum recommended exit velocity for industrial chimneys is limited to 30 meters per second in case of industrial chimneys with brick liners, whereas the maximum recommended exit velocity VE, V subscript E superscript max, is limited to 45 meters per second for industrial chimneys with steel liners. Hence, concluding our discussion on the functional design parameter, that is the exit velocity, which is also the most important functional design parameter that is considered in the functional design stage of the industrial chimney, the other functional design parameters that are also considered in the functional design stage of the industrial chimneys, in addition to the exit velocity, are the shape and the base dimensions of the chimney, which is a common and overlapping parameter with the structural design stage of the industrial chimney, as mentioned earlier. And the exit size of the industrial chimney, as well as the physical height of the industrial chimney, all of which, that is the shape and base dimensions, the exit size and the physical height of the industrial chimney, are common and overlapping parameters that are common to both the functional design as well as structural design of the industrial chimney. A brief overview of the physical relevance and the design implications of the functional design parameters numbered as Roman numerals 2, 3, and 4, that is the shape and base dimensions, the exit size, and the physical height of the chimney, is presented in the annexure at the end of the current lecture series. Proceeding to the second stage of the design process for industrial chimneys, that is the structural design stage. In the second phase of the design process, that is the structural design phase, the chimney shell or the chimney wall is dimensioned and designed to ensure that the design axial forces and design bending moments in the chimney shell at the base of the chimney, due to the various design load combinations as specified by the Indian Standard Code of Design Practice for circular cylindrical chimneys, IS 4998 Part 1, do not exceed the ultimate values or the corresponding ultimate axial forces and bending moments respectively for the chimney shell. And for the purposes of the structural design of the chimney shell, based on the limit state method of structural design, IS 4998 Part 1 specifies the following design loading combinations, which will be presented in the next slide. Continuing our discussion on the structural design stage of the industrial chimney, wherein the structural design phase for the industrial chimney is essentially based on the structural analysis and design of the chimney shell or the chimney wall, and the various design loading combinations that are to be considered for the structural analysis and structural design of the chimney shell as specified by the Indian Standard Code of Design Practice for circular cylindrical industrial chimneys, IS 4998 Part 1, are as follows. A. Dead load, including the self-weight of the chimney shell, the chimney lining, and accessories, based on the unit weights of the respective materials provided by IS 875 Part 1, the latest revision. B. The dead load combined with the wind load, that is abbreviated as DL plus WL, wherein the wind load is calculated as per the provisions of IS 875 Part 3, the latest revision, that is the 2016 revision, rather the 2015 revision, which is the Indian Standard Code of Design Practice for calculation of wind loading on structures. C. Dead load, DL, and abbreviation combined with earthquake load, abbreviated as EL, wherein the earthquake load is calculated as per the design criteria specified by the Indian Standard Code of Design Practice for earthquake resistant design of structures, that is IS 1893 2016 revision. D. The dead load plus the temperature load, abbreviated as TL, also calculated as per IS 4998, but Part 2 of the Indian Standard Code of Design Practice for circular cylindrical chimneys, which is presently in draft version and has not yet been enforced. E. The design load combination consisting of the dead load DL plus the wind load WL plus the temperature load TL, and F. The design load combination consisting of the dead load DL, the earthquake load EL, and the temperature load TL. It is worthwhile to mention here that the various design loading combinations consider only one of the two lateral or transverse loads, that is one of the two environmental lateral loads, either the wind load WL or the earthquake load CVL. Proceeding to the discussion on the various components of the design loading combinations that are specified by IS 4998, the Indian Standard Code of Design Practice for Circular Cylindrical Chimneys, we will begin with the most dominant or the predominant design load that governs the structural design of the industrial chimney or chimney structures in general. Now, as the wind loading on the chimney structures is one of the most dominant loads that dictate the structural design of the chimney shell. And as a consequence, chimneys are therefore also commonly referred to as wind resisting structures, since wind load is the predominant external force that governs the structural design of the chimney shell. Now, as a recap, to refresh your memory on the fundamentals of fluid mechanics that constitute the theoretical basis for the design specifications provided by the Indian Standard Criteria or Indian Standard Codes of Design Practice for calculation of wind loads on industrial chimneys and building structures in general. One of the first principles of fluid mechanics that forms the theoretical basis of the design formulations for calculating the design wind loads on chimney structures or building structures in general is that wind is air or fluid in motion. Therefore, exerts a drag and a lift acting on any single stationary fluff body, obstructing the streamlined flow of fluid, that is the airstream in the context of wind, where air is the fluid in the present context, and the drag and lift that are exerted on any single stationary bluff body obstructing a streamlined flow of fluid, for example, a chimney structure, that is the industrial chimney, in field of airflow or wind flow, thus obstructing the flow of air or the fluid, results in an along wind force and a crosswind force, respectively, due to the drag and lift that are formulated in the fundamentals of fluid mechanics, recall that the drag with lift, that is abbreviated as capital F subscript D or L as applicable, at any height Z of a single stationary block body obstructing a streamlined flow of fluid, for example, air in the context of wind or airflow, may be calculated as half the drag or lift coefficient as applicable times the fluid density, which is the air density in the context of wind or airflow, times the square of the wind speed, that is the speed of the fluid or the air speed at the relevant height Z under consideration, times the normal area, that is the area of the single stationary block body, which is the industrial chimney in the context of the wind flow, wherein the drag or lift coefficient, that is denoted as capital C subscript D or L as applicable, are provided by the fundamentals of fluid mechanics. In terms in the classical formulation for drag or lift based on the first principles of fluid mechanics, by dividing the drag or lift force, that is F subscript D or L as applicable, by the normal area, that is the area of the single stationary block body projected normal to the flow of the fluid or airflow in the context of the wind, the pressure, the fluid pressure due to the drag or lift may be calculated as half the drag or lift coefficient times the fluid density times the square of the speed of the fluid or the air speed in the context of the wind. Compare this equation with the along wind pressure or the desired wind pressure that is specified for the building structures or industrial structures or industrial chimneys in the present context, as provided by IS 875 Part 3, the Indian Standard Code of Design Practice for Calculation of Wind Loads, or IS 4998, the Indian Standard Code of Design Practice for Circular Cylindrical Chimneys. The along wind pressure for a unit value of the drag coefficient CD, that is in the direction of the wind, is given as half rho A, that is the air density or the density of the fluid or air in the context of wind, times the square of the wind speed at the relevant height above the mean ground level that is under consideration for calculating the along wind pressure. Noting that the air density or the density of the fluid or air, that is the fluid in the context of wind, is 1.2 in SI units, the design wind pressure for a unit value of the drag coefficient CD, that is CD equal to 1, in the along wind direction is specified, therefore, by the Indian Standard Codes of Practice at any height Z above the mean ground level as equal to 0.6 times the square of the wind speed, that is the design wind speed, Vz, at the relevant height of consideration, and the coefficient 0.6 in the design formulation for the design wind pressure in the along wind direction, Pz, is derived mathematically from the first principles of fluid mechanics based on the formulations of the drag and the related fluid pressure by substituting the value of 0.6 for the parameters or coefficients half times the air density. Thus, mathematically, proving that the design wind pressure that is specified by the Indian Standard Codes of Practice for calculation of wind loads on building structures and industrial chimneys, as presented by the design formulation, is based on the theoretical formulation for the along wind pressure that is derived on the basis of the first principles or fundamentals of fluid mechanics, that is the theoretical formulation for drag and the related fluid pressure on the basis of the first principles of fluid mechanics. Continuing our discussion on wind loading acting on industrial chimneys and the design wind loads that are to be considered in the structural analysis and structural design of the chimney shell in the industrial chimneys. The calculation of the along wind load as per IS 4998 Part 1, the Indian Standard Code of Design Practice for circular cylindrical chimneys, and IS 875 Part 3, the latest revision 2016 of the Indian Standard Code of Design Practice for wind loading on building structures in general. The IS codes of design practice for the structural design of circular cylindrical chimneys provide the along wind force denoted as F subscript Z, where the notation F denotes the wind force, while the subscript Z signifies the height above the mean ground level at which the wind force or the along wind force is to be calculated as the product of the drag coefficient times the design wind pressure as specified by IS 875 Part 3 2016 times the area of the industrial chimney projected normal to the direction of the wind flow. Since in general circular cylindrical chimneys are tapered or provided with a taper with varying areas of or surface areas projected normal or orthogonal to the wind direction along the height Z of the industrial chimney above the ground, the along wind force at any height Z, denoted as Fz, needs to be calculated incrementally or differentially, considering differential or segmental areas of the industrial chimney at the relevant height Z of interest for the segment of the surface area delta A subscript I, that is normal to the wind flow, wherein the segmental or the incremental or differential area delta AI is the area of the segment delta Z of the industrial chimney projected normal to the wind flow. Further, the drag coefficient denoted as C subscript capital D for a cylinder as the single stationary bluff body obstructing the wind flow or flow of fluid, that is air in the context of wind, is to be considered as 0.7 for cylindrical chimneys. Hence, with reference to the assignment question, that is the question presented in assignment number 4, the surface area of the industrial chimney under consideration in assignment number 4 may be discretized or subdivided into segmental areas, or the height, that is the overall or physical height of the industrial chimney that is considered in assignment number 4 may be subdivided into segments numbered using the index I, where I ranges from 1 to 10, since the minimum number of segments that need to be considered for an industrial chimney for calculation of along wind load as per IS 4998 part 1 are 10. Therefore, subdividing or discretizing the height of the chimney into 10 segments, in effect discretizing or subdividing the surface area of the industrial chimney normal to the wind direction or wind flow into 10 segmental or differential areas delta AI as presented in the table displayed in the current slide. We will proceed to calculate the segmental or differential along wind force delta FZI on each of the segments or increments. As one can note from the table presented in the current slide, the total height or the overall physical height of the chimney, that is 200 meters, is subdivided into 10 ranges, that is based, the subdivision being based on the non-linearity of the distribution of the design wind pressure over the height from the mean ground level. Therefore, smaller subdivisions are considered, that is, smaller height ranges or ranges, smaller range or sub-ranges of heights are considered closer to the ground level. For example, 0 to 5 meter, 5 to 10 meter, 10 to 15 meter, and 15 to 20 meter, since the design wind pressure above the mean ground level or the design wind speed above the mean ground level exhibits maximum non-linearity up to the height of 20 meters above the mean ground level, which is the gradient height, wherein the wind speed exhibits the maximum non-linearity with respect to the height up to the gradient height of approximately 20 meters. Beyond 20 meters, that is above 20 meters, the increments or the subranges of height that are considered for calculating the along wind force at any general height Z acting on the industrial chimney is increased to 20 meters. Thus, the subranges of the height or the increments in height that are considered above the gradient height of 20 meters are 20 to 40 meters, 40 to 80 meters, 80 to 120 meters, 120 to 160 meters, and 160 to 200 meters, which is the maximum height at the top of the industrial chimney. And the increase in the subranges or the increments or the segmental heights above the gradient height of 20 meters is due to the physical reality that the gradient in the wind speed above the mean ground level is maximum up to the gradient height of 20 meters, above which the gradient or the rate of change of the wind speed with respect to height decreases, and the wind speed, the non-linearity in the variation of the wind speed above the gradient height of 20 meters is much less than the gradient or the non-linearity in the variation of the wind speed below the gradient height of 20 meters. Further, the next column in the table presents the average or the mean height in the subrange of the height under consideration, or the segment of the surface area of the industrial chimney normal to the wind direction under consideration, and is simply obtained as the average of the upper and lower limits of the subrange of the height in the relevant segment I. The segmental or the differential area, that is the differential area of the segment of the industrial chimney normal to the wind flow, wind direction in the respective segment number I is calculated in the third column simply as the range or subrange of the height times the width BI, that is the average width of the segment of the industrial chimney at the average height, since the the width of the chimney normal to the wind direction varies along the height due to the taper that is provided in the cross-sectional shape or the vertical elevation of the industrial chimney. The next column in the table requires the calculation of the factor K2 in the design formulation for the design wind speed Vz, and is termed as the terrain height and size factor as per IS 875 Part 3 2016, and therefore needs to be calculated for each segment separately, since the factor K2 in the design formulation for the design wind speed provided by IS 875 Part 3 is a function of the height Z above the mean ground level, and therefore accounts for the variation of the wind speed along the height above the mean ground level in the atmospheric boundary layer, wherein the ground is the boundary. Referring to Table 2 of IS 875 Part 3, the terrain height and size factor K2, which is a function of the height Z above the mean ground level, may be calculated in provided in the column for the factor K2 corresponding to the height Zi above the mean ground level at the mid height or the average or the mean height Zi of the relevant segment of the industrial chimney that is under consideration. The factors K1, K2, factors K1 and K3 and K4 that are the multipliers or coefficients in the design formulation for the design wind speed at any given height Zi are termed as the risk or probability factor K1, the topography factor K3, and another factor K4 as per IS 875 Part 3 2016 revision, the latest revision, which is a factor that accounts for cyclonic vulnerability of the region or site of construction while the parameter VB, that is capital V subscript B, represents the basic wind speed given by the wind speed map of India, that is illustrated in figure 1 of IS 875 part 3 2016 revision. Hence, substituting the relevant coefficients K1, K3 and K4, which are the risk or probability factor and the topography factor and the cyclonic region factor respectively, as well as the basic wind speed VB from the wind speed map of India presented in figure 1 of IEC 875 part 3. One can fill in the design wind speeds denoted as VZI corresponding to the relevant average or mean height ZI for the various segments I numbered from 1 to 10 in the column of the table corresponding to the design wind speed, and similarly the design wind pressure at the relevant heights ZI may be calculated by multiplying the design wind speed VZI computed in the previous column of the table by 0.6 and filling in the design wind pressure PZI, where the subscript small p, where the notation small p denotes the design wind pressure, the subscript Z denotes the height Z above the mean ground level, and the subscript I denotes the segment number I of the surface area or the sub-range of the height into which the industrial chimney or the elevation of the industrial chimney is subdivided or discretized. Finally, the along wind force or the acting on the segment I of the surface area of the industrial chimney, normal or perpendicular to the wind direction, with the mean or average height Zi may be calculated as the design wind pressure obtained in the previous column for the particular segment I times the segmental or differential area delta AI calculated in one of the previous columns times the drag coefficient for the shape of the industrial chimney, which is given as 0.7 for a circular cylindrical chimney by IS 4998 part 1, while the bending moments above the base of the chimney may be simply computed as for each segment I, that is the segments I equal 1 to 10, into which the total surface area of the industrial chimney or the elevation of the industrial chimney is subdivided or discretized, may be calculated by multiplying the segmental or differential along force delta Fzi obtained in the previous column by the average or the mean height Zi of the respective segment. The total shear force or allongment force at the base of the chimney may be obtained by simply adding or summating the segmental or differential allongment forces acting on each of the segments I numbered from 1 to 10, into which the elevation or the total surface area of the industrial chimney is subdivided, while the total bending moment or the overturning moment at the base of the industrial chimney may be obtained by summating the segmental or differential bending moments delta Mzi corresponding to the various segments I numbering from 1 to 10, into which the total elevation of the total surface area of the industrial chimney normal to the wind direction is discretized or subdivided. In general, the shear force due to the wind load acting on any cross section at say any height corresponding to the lower limit of the sub range of heights may be calculated by summating the segmental or differential allongment forces delta Fzi for all the segments say I equal to 1 to I minus 1 in order to calculate the shear force due to the allongment force at the height of say 40 meters, which is the lower limiting value of the height for the sub-range or segment I minus 1. Similarly, the bending moment or the overturning moment for any cross-section of the industrial chimney at the lower limiting value of the height corresponding to segment I minus 1, for example, in this case being 40 meters, can be calculated by summating the segmental or differential bending moments for all the segments I numbering I from 1 to I minus 1, into which the surface area of the industrial chimney, normal or perpendicular to the wind direction, is subdivided or discretized. The structural behavior of the chimney shell, that is the circular cylindrical shell of the industrial chimney, subjected to the wind loading, may be classified into two fundamentally distinct types of shell response under the action of the wind load. One, longitudinal bending of the shell that occurs due to the bending moment mzj, that is also known as the meridional bending moment in the notation of the theory of cylindrical shells, induced at any section J at height Zj above the mean ground level MGL, due to the force resultant Fzi of the along wind pressure distribution Pz, that is the distribution of the along wind pressure above the mean ground level, and specifically the section I that is the section of interest at which the bending moment or the meridional bending moment mzj is to be calculated. The second fundamentally distinct component or type of structural response that is exhibited by the circular cylindrical shell in the industrial chimney under the action of wind loading is the circumferential bending of the shell that occurs due to the radial distribution of the wind pressure at any cross section of the chimney as depicted visually by figure 3.4 of the annexure presented at the end of the lecture notes for the present lecture series, as depicted by figure 3.4 of the annexure presented at the end of the lecture notes corresponding to the current lecture series. The radial pressure distribution P that is due to the wind pressure is a function of theta, that is the angle of incidence or the angle with respect to the wind direction. And as illustrated by the figure depicting the radial pressure distribution due to the wind pressure over the circumference of the cross-section of the industrial chimney under consideration, the radial pressure distribution P, defined as a function of theta, that is the angle of the point on the circumference under consideration with respect to the direction of the wind, depends on a few factors. One, that is Roman numeral 1, the shape of the chimney. In case the chimney has a non-circular shape, however, the scope of the present discussion includes only circular cylindrical chimneys, and therefore the particular factor, that is the shape of the chimney, in the scope of the present course is not relevant, since we are discussing only circular cylindrical chimneys. However, in general, the radial pressure distribution due to the wind over the circumference of or the periphery of any industrial chimney will also depend on the shape of the chimney, that is the cross-sectional shape of the chimney, which may be non-circular in general. Further, in case of general cross-sectional shapes of the industrial chimney, for example, non-circular shapes, the aspect ratio of the shape, that is the ratio of the width to the depth of the shape, will also be one of the governing parameters that determine the radial pressure distribution over the periphery of the cross-section of the chimney. 3. The angle of incidence of the wind. And 4. The Reynolds number, denoted as R subscript E, of the fluid flow, that is the Reynolds number of the flow of air or the fluid around the industrial chimney. In case of the circular cylindrical chimneys, which are in the scope of the present course, therefore only the angle of incidence of the wind, that is theta, with respect to the point on the circumference of the cross-section of the industrial chimney and the Reynolds number of the flow of fluid, that is Reynolds number of the airflow, are pertinent by virtue of the circular shape of the chimney. Before we proceed to the next slide, discussing the structural behavior of the chimney shell under the action of the wind load on the circular cylindrical chimneys, it is worthwhile to note here that the shear force Vz or Vs, denoted as Vs, at the base of the industrial chimney, that is at the height z equal to 0 about the mean ground level, may be calculated as the summation of the force resultant of the along wind pressure distribution depicted by the curve in blue ink on the figure in the current slide above the base that acts on the surface area of the industrial chimney above the base of the chimney. In general, the shear force due to the along wind pressure distribution at any cross section I, denoted as Vs or capital V subscript S, I, may be calculated as the summation of the force resultant or the integration of the force resultant of the along wind pressure distribution acting on the surface area above the section I of interest at which the shear force is to be calculated. Further, the longitudinal or meridional bending moment MZI may be calculated at any general cross section I of the industrial chimney by summating the product of the incremental or differential or segmental along wind forces acting on all the segments above the section I of interest up to the top of the industrial chimney. In other words, the longitudinal or meridional bending moment MZI at any cross section, that is horizontal cross section I of the industrial chimney, may be computed by integrating the force resultants times the lever arm of the force resultant of the alignment pressure distribution above the section I of interest at which the longitudinal or meridional bending moment is to be calculated. Continuing our discussion on the structural response or structural behavior of the chimney shell subjected to wind pressure, the second fundamental component or the second type of structural response of the chimney shell in the industrial chimney subjected to wind pressure is the circumferential bending of the chimney shell that is caused by the radial pressure distribution over the periphery or the circumference of the chimney cross section at the given or specific height of interest, thus generating a circumferential bending moment denoted as m theta, that is capital M subscript theta, in the notation of the theory of shells discussed earlier in the course in the context of cylindrical shell structures. The radial pressure distribution P as a function of theta, where theta is the angle of the point of interest on the periphery or the circumference of the chimney cross section at the relevant height of interest, depends on the Reynolds number, where the Reynolds number denoted as capital R subscript E is generally in the ultracritical range in the practical or real situation of wind flow, that is mathematically the Reynolds number denoted as R subscript E is greater than the critical Reynolds number R subscript E superscript CR that requires, that is the critical Reynolds number for turbulent flow. In other words, the wind flow and the resultant radial pressure distribution P theta over the circumference or the periphery of the circular cylindrical chimney at any cross section is a turbulent flow, and hence the related radial pressure distribution due to the wind pressure over the circumference or the periphery of the cross section of the industrial chimney at the height of interest is typically corresponding to a Reynolds number value in the ultracritical range, that is the range of the turbulent flow of fluids. As one can observe from the figure presented in the current slide that depicts qualitatively the radial pressure distribution denoted as small p as a function of theta, where theta is the angle of the point of interest on the circumference or periphery of the circular cylindrical shape of the cross section from the angle of the wind direction. The radial pressure distribution is positive up to certain values of the angle theta from the wind direction, whereas beyond the windward side of the cross section, the wind pressure, that is the radial pressure distribution due to the wind, becomes negative, which implies that the radial pressure distribution on the leeward side of the periphery or circumference of the cross section of the circular cylindrical shape is negative, implying suction on the negative or the leeward side of the circular cylindrical shape or periphery of the industrial chimney. The pressure distribution, that is the radial pressure distribution P theta, was experimentally measured for a cylinder in a flow of fluid with a high value of Reynolds number in the ultracritical range, that is in the range of turbulent flow of fluid, and assuming that the along wind force resultant of the wind pressure distribution P theta is balanced by the shear forces in the shell, the magnitude and the direction of the maximum bending moments, that is, the maximum positive and bending moments in the circumferential bending of the shell, that is, the maximum positive and negative circumferential bending moments m theta, and the maximum axial force n theta in the circular cylindrical shell, in case of the circular cylindrical industrial chimney, can be determined by implementing the coefficients that are provided in table 3.3 of the annexure presented at the end of the lecture notes corresponding to the present lecture series, which were or have been obtained from the theory of shells based on the idealization that the shear forces vary sinusoidally over the circumference of the shell. Hence, referring to the annexure, one can apply the coefficients for the maximum positive and maximum negative bending moments due to circumferential bending of the chimney shell under the action of the wind pressure, as well as the maximum axial force n theta, to calculate the maximum positive and maximum negative circumferential bending moments m theta and the maximum tangential or circumferential axial force n theta by applying the coefficients provided in table 3.3 of the annexure presented at the end of the lecture notes corresponding to the present lecture series, that are conceptually derived from the theory of cylindrical shells based on the idealization that the shear forces induced in the cylindrical shell vary sinusoidally over the circumference of the shell.